Electricity and magnetism are connected forces. They interact in specific predictable ways, forming the foundation of electromagnetism. The study of electromagnetism starts with observing magnetic fields and how they respond to electrical currents. These principles explain everyday technologies, such as electromagnets and electric motors. Electromagnets are created by running current through a wire, producing a magnetic field. Electric motors use the interaction between magnetic fields and electrical current to produce motion. This powers appliances, machinery, and home safety systems. Understanding electromagnetism helps us see how these forces work together in real-world applications. Hans Christian Ørsted was a Danish physicist. He lived from 1777 to 1851. In 1820, Ørsted made a discovery that changed physics. He found that a compass needle moves when near a wire with electric current. This showed the connection between electricity and magnetism. It started the field of electromagnetism. The discovery showed that electric current in a metal conductor creates a magnetic effect. This works both ways. Electricity, magnetism, and moving magnets make electric currents. This connection is a foundation of modern physics and electrical engineering. The unit of magnetic field strength is named after Ørsted. The Ørsted. A magnetic field surrounds a magnet and is where its force can be detected. It has magnitude and direction. Scientists use imaginary lines called magnetic field lines to visualize these fields. These lines show the path a free north pole would follow in the field. Every magnet has two poles, north-seeking and south-seeking. The north-seeking pole points toward Earth's geographic north, and the south-seeking pole points toward the geographic south. Magnetic field lines emerge from the North Pole and merge at the South Pole, creating closed curves inside the magnet. Closer lines mean a stronger field, while wider spacing means a weaker field. Field lines never intersect, and iron filings can be used to visualize field patterns by aligning along the lines when sprinkled around a magnet. Electric current, flowing through a straight metallic conductor, creates a circular magnetic field. The field strength increases with more current and decreases with distance. Changing the current's direction reverses the field's direction. The right-hand thumb rule helps determine the field's direction. Hold the conductor with your thumb pointing in the current's direction, and your curled fingers show the field's direction. This rule also applies to circular loops and coils. In a coil, each turn adds to the field, making it stronger inside than outside. A solenoid, a coil of many turns, produces a uniform magnetic field inside, similar to a bar magnet. An electromagnet is made from a soft iron core with a coil of insulated copper wire. When electric current passes through the wire, the soft iron core becomes magnetized. This happens because the coil creates a strong magnetic field. The magnetization is not permanent. When the current stops, the magnetic effect disappears. This makes electromagnets useful in many devices. They are used in electric bells, loudspeakers, and electric cranes. These devices rely on electromagnets to turn a magnetic field on and off. Electromagnets are found in many everyday devices that need to control a magnetic field. André-Marie Ampère discovered that a magnet exerts force on a current-carrying conductor. This happened in the early 1800s. In an experiment, an aluminium rod with current is placed between magnet poles. The rod moves perpendicular to the current and magnetic field. Reversing the current or magnetic field reverses the force direction. The force is strongest when current and magnetic field are perpendicular. Fleming's left-hand rule determines the force direction. You point your forefinger at the magnetic field, middle finger at the current, and your thumb shows the force direction. This principle is used in electric motors, generators, loudspeakers, microphones, and measuring instruments like galvanometers. Your home's electricity comes through three main wires: live, neutral, and earth. The live wire carries 220 volts. The neutral wire completes the circuit, and the earth wire connects to a metal plate in the ground for safety. Electricity enters your house through a meter board with a main switch. The system then branches into separate circuits, 15 ampere for high-power appliances and 5 ampere for lower-power devices. Each appliance connects in parallel and has its own switch. Safety features include an electric fuse that melts when overloaded, and the earth wire that provides a low-resistance path to ground, preventing electric shock. A short circuit occurs when the live and neutral wires touch directly. This can happen due to damaged insulation or appliance problems. When the wires touch, the circuit resistance drops and the current increases sharply. Overloading is another type of electrical fault. It happens when a circuit is overloaded. This can occur if the supply voltage increases, or if too many appliances are connected to one socket, or if multiple high-powered devices are used on the same circuit. To prevent overloading, use the correct fuse ratings and spread appliances across multiple circuits. Avoid plugging multiple high-powered devices into one socket. Regularly inspect wiring insulation to prevent electrical problems. A magnetic field is the area around a magnet where its force can be detected. It's measured as a vector quantity. Magnetic field lines show the direction and magnitude of the field. A solenoid is a coil of many insulated turns in a cylindrical shape. Adding a soft iron core and passing current through, it creates an electromagnet. There are rules to work with magnetic fields and current. Fleming's left-hand rule determines the force direction on a conductor in a magnetic field. The right-hand thumb rule shows the magnetic field direction around a current-carrying wire. Two common electrical faults are short circuits and overloading. A short circuit occurs when live and neutral wires touch, causing excessive current. Overloading happens when too much current flows, often due to too many appliances or too much voltage. The strength of a magnetic field depends on several factors. Increasing the current through a conductor makes the magnetic field stronger. More current equals a stronger magnetic field. The distance from the conductor also affects the field. Moving further away weakens the magnetic field. Wrapping the conductor into a coil adds to the field's strength. More turns mean a stronger magnetic field. The force on a current-carrying conductor in a magnetic field acts perpendicular to both the current and the field. Fleming's left-hand rule helps predict the direction of this force. This material follows on from what you learned about electricity, specifically how electric current produces heat. You'll see fuse principles again, which use heat from current to protect circuits. This knowledge will help you understand electric motors, generators, and other topics later on. These topics rely on the magnetic and electrical principles covered here. Electromagnetic principles are used in medical imaging technology like MRI machines. Electric transportation, including trains and cars, relies on motors and generators. Industrial machinery uses electromagnetic induction. Household safety systems, like fuses, use heat-based current detection. These applications connect back to the fundamental principles in this chapter.